Welcome back to MCB 170, Society and the Brain. This is lecture 27, which corresponds to part 1 of module 14. The title of module 14 is Happiness. In part 1, we'll be discussing the neurobiological aspects of happiness. In part 2, we'll switch to the psychological and sociological aspects. What exactly is happiness? Well, you could say that happiness is feeling good, enjoying life, and preferring things as they are. This is like the contentment definition of happiness. It turns out that happiness researchers are divided concerning exactly what happiness is. Most happiness researchers believe that happiness has more than one component, that it's not a single thing. And the consensus seems to be that happiness has two components, pleasure and satisfaction. Satisfaction is basically pride. It's the pride you feel in your accomplishments, in your life, in yourself. Satisfaction involves an appraisal of your own life and often a comparison of your life with the lives of other people. Satisfaction is derived through a controlled process. Pleasure is a little simpler. Pleasure is basically joy. It's the joy you feel when you're eating your favorite ice cream in the company of your favorite person. Pleasure is a more automatic process. If you want to experience intense pleasure, ecstasy even, apparently all you have to do is pop a pill. The drug methylene dioxymethamphetamine, abbreviated MDMA, is known commonly as ecstasy, or E, or Molly. It's based on the amphetamine molecule. Amphetamine is the most common psychostimulant. It's the main ingredient in Adderall. Methamphetamine, as you probably know, is a common drug of abuse, a more powerful psychostimulant than amphetamine itself. MDMA, ecstasy, is methylene dioxymethamphetamine. It's like a super souped up version of amphetamine. Here's its chemical structure. As you may know from chemistry, whenever you view the structure of a biomolecule and there's an unlabeled vertex, that's a carbon atom. So all of these vertices are carbon atoms. A carbon atom has valence 4. It can make four chemical bonds. If you ever see a vertex that doesn't have 4 lines going to it, it's assumed that that carbon is making bonds with hydrogen atoms. So MDMA is this relatively simple molecule composed mostly of carbons and hydrogens with a couple of oxygens and a nitrogen. It gets compressed into these little pills, which are available illicitly. Here's a whimsical cereal called Honey Nut Ecstasy, sweetened whole grain oat cereal with pure MDMA and almonds. Each box comes with a free glow stick. And the little bee who advertises it is wearing his pacifier. So how does this work? How does a simple molecule make us feel ecstatic? Well, here's the diagram we've shown many times in the course, the noradrenergic and serotonergic synapses. We generally talk about one or the other, but today we're going to talk about both of them at the same time. Remember that the noradrenergic synapse first produces dopamine, which is then converted into noradrenaline. So that the noradrenergic synapse can represent both the dopaminergic synapses and the noradrenergic synapses. We know that in both cases, these neurons absorb certain amino acids, convert them into their transmitter, and secrete their transmitter onto postsynaptic neurons. And that transmitter, once released, can be taken back up. It can be reuptaken into the synaptic terminal. So what does MDMA do? Well, MDMA is taken up by the transporters. MDMA is taken up by the dopamine, noradrenaline, and serotonin transporters. It's brought into the terminal, and then it makes those transporters run backward. So it actually forces dopamine and noradrenaline and serotonin out of synapses and floods the brain with the monoaminergic neurotransmitters. Recall, the big three monoaminergic neurotransmitters are dopamine, noradrenaline, and serotonin. So MDMA causes your synapses to release, to dump out all their dopamine, noradrenaline, and serotonin. And the MDMA-induced increase in serotonin secondarily increases secretion of oxytocin. Oxytocin, recall, is a peptide neurohormone associated with feelings of closeness, of empathy, of warmth. So on MDMA, your brain is flooded with the monoaminergic neurotransmitters, dopamine, noradrenaline, serotonin, and the neurohormone oxytocin. And this can account for its effects. What are the acute effects of MDMA? Well, the acute effects are the immediate effects, the immediate main effects. The acute effects are the effects that people take the drug for. The acute effects of MDMA include euphoria and enhanced mood, probably due to dopamine, well-being, happiness, probably due to serotonin, increased energy, probably due to noradrenaline, extroversion, feeling close to others, increased empathy, increased sociability, probably due to oxytocin, changed perception of colors and sounds, and moderate derealization, but not hallucinations, probably due to serotonin, maybe combined with dopamine. Recall that the classical hallucinogens work mainly by increasing serotonergic and dopaminergic tone. MDMA is not a hallucinogen, but it does produce some mild hallucinations. That's why the silly cereal comes with a free glow stick, because one of the hallucinations that MDMA shares with classical hallucinogens are trails. If you look at a bright moving light in a dark room and you're under the influence of a classical hallucinogen or ecstasy, you'll see a trail following that light. MDMA has certain acute side effects. These are immediate effects that are different from the main effect. They include jaw clenching and dry mouth and thirst. That's why the little bee had a pacifier. Also restlessness, lack of appetite, etc., palpitations. Things that are mostly annoying, but some can be serious, like hot flashes, for example. There are deaths associated with acute ingestion of ecstasy, due mainly to overheating and dehydration. So individuals who use ecstasy, and you shouldn't because it's dangerous and against the law, need to be careful that they don't get overheated and that they maintain hydration. MDMA also has certain after effects that can last up to 7 days after MDMA use. They include fatigue, lack of energy, and irritability, kind of the reverse of the great feelings that you feel when you're on ecstasy. They can also include anxiety and depression. So individuals prone to depression can get seriously depressed in the days following an MDMA experience. And heavy use, frequent use of high doses of MDMA has been associated with deficits in long and short-term memory and other cognitive functions. So MDMA use can be dangerous. The classical hallucinogens, ironically, don't seem to have adverse health consequences. MDMA does apparently have adverse health consequences. In fact, there's a debate still among researchers as to whether or not MDMA can kill monoaminergic, especially serotonergic, nerve terminals. It's not clear whether it does or not, whether it causes lasting brain damage, but it can cause these cognitive deficits with heavy frequent use. Fortunately, there are safer ways to feel happy and positive. One is laughter and humor. According to Gervais and Wilson, and this is not Ricky Gervais, it's Matthew Gervais, laughter benefits both the sender and the receiver. Laughter can spread positive emotions, promote security and stability, decrease negativity, moderate stress, and strengthen group identity and cohesion. All very nice. And there's some evidence that positive affect can contribute to good health. So what's the purpose of positive affect? Well, Fredrickson explored the adaptive value of positive affect by comparing it to negative affect. So he compared positive affect or emotions with negative affect or emotions. And they said that, negative emotions like fear are adaptive because they promote survival-oriented responses. If a situation is bad and possibly threatening, you need to get yourself out of there. You're experiencing negative emotions which motivate you to escape. On the other hand, the adaptive value of positive affect and humor is to promote a broadening of response, to provide a way to explore new possibilities in an atmosphere of security and safety. I'm often amazed at the difficult topics that comedians can raise. Things that you wouldn't talk about, especially not in public, especially not in a room full of strangers, under other circumstances, you might be willing to consider in a comedy show where everyone's sort of laughing and happy and experiencing positive emotions, positive affect. It's broadening their response. They're willing to explore new possibilities and new ways of thinking in that humorous context. So you would suppose that positive affect and humor and laughter would activate the pleasure and reward system. And it does, but showing that has been tricky. Brain scans show that positive emotions are associated with activity of many brain regions, and we'll get to some of those. And it's reasonable to suppose that they include regions involved in pleasure and reward, and they do. So let's consider the pleasure and reward system again in detail. As you know, the major reward system in the brain is the dopamine system, and the majority of dopamine-containing neurons in the brain are located in the substantia nigra and the ventral tegmental area. The striatum is the main target for projections from these structures. The substantia nigra sends a major projection to the dorsal striatum, while the ventral tegmental area sends a major projection to the ventral striatum, and the key structure there is nucleus accumbens, but there are also other ones. And as we've discussed before, the ventral tegmental area, VTA, also projects heavily to the limbic system and cerebral cortex. This is a slide we've shown before, showing the dopamine system, the so-called mesolimbic dopamine system. Here we have the dopamine-containing neurons, both in substantia nigra and ventral tegmental area. Substantia nigra sends a heavy projection to the dorsal striatum, caudate and putamen, and it's involved mostly in movement control, movement initiation. Ventral tegmental area is a little smaller, and it projects more diffusely to lower and higher regions in the brain, and it projects throughout the limbic system and cerebral cortex. The ventral tegmental area is kind of the battery of the reward system. This is another diagram we've shown many times, the ventral tegmental area projecting to ventral striatum and specifically to the nucleus accumbens. Secretion of dopamine into nucleus accumbens is associated with pleasure. And it also with other structures. Secretion of dopamine from ventral tegmental area into other structures, including the septum, also is associated with pleasure. So the nucleus accumbens isn't the only place that mediates pleasure in the brain. There are other similar places. But nucleus accumbens is the key structure. Here's what these places look like on an MRI scan. This is a structural scan. Shown in pink is the substantia nigra. Shown in yellow is the ventral tegmental area. You can see that the substantia nigra is bigger than the ventral tegmental area. The substantia nigra projects to the dorsal striatum, and it's involved mainly in movement initiation. Ventral striatum is involved in pleasure and reward and projects to the ventral striatum, shown in blue, which is mainly the nucleus accumbens, but not only nucleus accumbens. Okay, it turns out that studies of positive affect and of laughter and humor in the past weren't able to show activation of the reward system, but a seminal study finally did. Now, if I tell you a joke and you laugh, Well, that joke is going to activate language areas in your brain involved in understanding the joke, and motor areas involved in actually producing the laughter. But Mobbs et al. Show that a funny cartoon also can activate the mesolimbic dopamine pathway. The language areas included the temporal-occipital junction and the inferior frontal gyrus. Inferior frontal gyrus includes Broca's area, and the laughter areas include the supplementary motor area. So these are areas involved in making mouth movements and tongue movements and laughter movements. But the temporo-occipital junction and regions of the brain near Broca's area are involved in the mirror neuron system and other parts of the brain that are involved in the theory of mind. Mirror neuron system, theory of mind, these are parts of the brain, high-level parts of the brain that mediate social cognition, that mediate feelings of empathizing and understanding others, and reasoning about the intentions and thoughts of other people. And we'll see this, that a lot of brain areas that are active when people feel positive emotions involve empathy and theory of mind, for good or ill. You know, if you feel good because other people feel good, that's kind of an empathic happiness. But if you feel good because you're using your theory of mind to compare your life with somebody else's life, that might have a more negative connotation. Yes, so these kinds of areas were active, these theory of mind and motor areas, but the reward areas were also active. They included the ventral tegmental area and the ventral striatum, mainly nucleus accumbens. Also activated paradoxically in this particular experiment was the amygdala, associated with fear. How did that happen? So in this particular experiment, the joke was a funny cartoon. And they manipulated these cartoons. So they found pairs of cartoons, here's an example, from newspapers that were supposedly funny, but they photoshopped them to remove the funny part. So the nice thing was that the subject saw essentially the same stimulus, same kind of stimulus configuration, but one was funny and the other wasn't. I personally don't find this particular cartoon very funny, but this illustrates their paradigm, which apparently was effective in showing clear activation of the reward center when people laughed and experienced humor. Here's a diagram depicting the brain scan results. You find certain regions in temporal lobe and Broca's area, inferior frontal gyrus are active, right? So is apparently the cingulate gyrus, anterior cingulate cortex, and the amygdala, but the main finding is activation of the mesolimbic reward regions, ventral tegmental area, and nucleus accumbens. Why? Why were these various regions active? Well, again, temporo-occipital junction, inferior frontal gyrus, these are probably mirror neuron theory of mind regions. Supplementary motor area, that's involved in actually producing the mouth movements and throat movements associated with laughter. Mesolimbic reward regions, ventral tegmental area and nucleus accumbens, clearly pleasure. Amygdala, fear. Well, Mobbs interpreted that finding as follows. They said that a joke often involves this setup that evokes stress, it evokes fear. It's kind of threatening almost. You know, like a good comedy show almost threatens you a little bit. But then when that threat is relieved, when that fear is relieved, you experience a positive affect. So, according to them, there is a little fear, a little stress associated with a good joke. When you find out that it's really just a joke, it increases your pleasure in the joke, but it initially involved a little bit of fear. So the feeling of happiness can involve, as we've observed in many other contexts, lots of different brain regions, right? It can involve a little fear. It can involve a little comparison of yourself with others. It can involve the worry that you're going to compare badly. But when that fear is relieved, you experience pleasure, and sure enough, it activates the reward area. Here's another study that looked at brain activity when hearing laughter and compared it with the brain activity when just hearing speech, regular speech. Regions that were active upon hearing laughter that were not activated when hearing regular speech included superior temporal gyrus, subcentral gyrus, Rolandic operculum, and Hessel's gyrus. Okay, I don't even know what these regions do, but the superior temporal gyrus is part of the mirror neuron circuit. And these authors thought that its involvement may be related to the contagiousness of laughter, kind of a sharing of positive affect through empathy. Other people are laughing, you're happy about that, that makes you happy too. So again, we see that in contexts that evoke a positive affect, it often does involve empathy and thinking about others, maybe in a positive way, maybe in a more negative comparison kind of way, maybe in a butt of the joke kind of way, maybe in a relief that you're not the butt of the joke kind of way. It's complicated. This is a study that I like very much by a group in Japan who tried to separate out the pride and joy components of happiness. They tried to separate satisfaction and pleasure in happiness. And the way they did that was they had their subjects, who were Japanese college students, read sentences that produced a feeling of pride or a feeling of joy. And they found that sentences that produced a feeling of pride activated the right temporal sulcus and left temporal pole. And again, these are regions associated with the theory of mind. So a person reads a sentence that makes them feel proud, and that's activating parts of the brain that are involved in thinking about others, in thinking about what others think. Interesting, expected activation of the prefrontal cortex was not observed. So these authors expected to find prefrontal cortex activated during the feeling of pride. It wasn't activated in pride. Prefrontal cortex is involved in positive feelings, however, we'll get to that toward the end of part one. In contrast, reading sentences that produced a feeling of joy activated the ventral striatum, the reward center. Also activated, ironically, the insula and operculum. Again, don't worry about the operculum. These sentences that evoked a feeling of joy activated the insula, which we know is associated with disgust. Why? Again, it's complicated. So here's an example. Here are examples of the sentences that evoked joy or pride. And they also had sentences that evoked a neutral feeling. Why? Because again, certain parts of the brain are going to be active when you read a sentence, no matter what the sentence is about, no matter how it makes you feel. And so what these researchers did was they looked at the brain activity when subjects read a neutral sentence, and that served as their control. Then they subtracted that activity from the brain activity that was evoked when a person read a sentence that evoked joy or read a sentence that evoked pride. So they were able to find the parts of the brain that were specific to joy and pride, and not just reading any old sentence. And these are funny. I like the neutral ones. I took a class at college. This was about as enjoyable as preparing for an examination or eating breakfast or buying a medicine for a cold. Sentences that evoked joy included I won the lottery or I ate my favorite cake. Sentences that induced pride included I was awarded a prize for my novel, I got a perfect score in mathematics. So again, this study was conducted in Japan, and the subjects were Japanese college students. They actually repeated this study here in the United States, in fact, right here at the University of Illinois. And all the different items were the same, except they had to add one. Ha 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 ha. Anyway, here are their results in terms of brain scans. Again, they subtracted the brain activity in the neutral case from the brain activity in the pride or the joy case, and were able to identify those parts of the brain specifically associated with pride or joy. And in you can see pride minus neutral, activation in right superior temporal sulcus and left temporal pole. And in B, joy minus neutral, activation in ventral striatum, insula, and anterior cingulate cortex. Again, what's the interpretation? Pride is activating parts of the brain involved in theory of mind. It involves an appraisal of your own life, a comparison of your life with other people's lives as a controlled process. Joy is more automatic. It involves the ventral striatum, pleasure. It also involves anterior cingulate conflict and insula disgust. Why is that? I don't know, we can speculate. Maybe that the joy that you experience when you're eating your favorite cake gets counterbalanced by the conflict and disgust you feel out of consuming all those calories. But these results were pretty consistent. They were pretty strong. In these two graphs, you see the rating of pride or joy, how proud or how joyful the subjects felt when reading those sentences, and the activity, either up in superior temporal sulcus or in the ventral striatum. Superior temporal sulcus for pride, ventral striatum for joy. These correlations are very high. This study, the results were very convincing. These are very high correlations for a fMRI study. So what about the prefrontal cortex? Well, the prefrontal cortex is involved also. In 2000, Richard Davidson showed subjects images of babies, either normal, healthy, or grossly diseased, and took fMRI images of their brains while they were viewing these pictures of either happy or sad babies. And the results were that the amount of happiness was positively and negatively correlated with activity in the left and right prefrontal cortex, respectively. So you see a happy baby, and through empathy or joy or whatever, you have a lot of activity in the left frontal cortex and decreased activity in the right frontal cortex. Or you see a baby who's diseased and unhealthy, unhappy, and there's a lot of activity in the right frontal cortex with decreased activity in the left prefrontal cortex. They also showed that happiness activates the left anterior temporal cortex. And I was skeptical of this finding when I first saw it, and I'll show you why. But apparently this finding has been reproduced many times, and now it's a well-established fact that if you feel happy, left prefrontal cortex increases activity, right prefrontal cortex decreases activity, and vice versa. So here's some pictures of the babies. Here's a normal, happy, healthy baby. This is a sad, diseased baby. And I want to point out that all of the diseased babies were photoshopped. So this isn't an actual image of a suffering baby. This is a grossly photoshopped picture of a baby. Anyway, this is what happened when they showed individuals these photographs while they were taking an fMRI scan of their brains. Let's take sad first, because I think the results are a little more clear. When individuals viewed the sad babies, they had increased activity in right prefrontal cortex, and that's very clearly shown here. When they showed happy babies, there was more activity in the left prefrontal cortex. Now, this activity is on the left-hand side of the brain, but it doesn't look like it's prefrontal cortex to me. This must be more temporal area. Anyway, they claimed that it was this difference in left and right prefrontal cortex that was apparent when individuals were happy because they saw happy babies, or sad because they showed sad and deformed babies. Despite that, and despite my misgivings, apparently this finding is so well established that bioengineers can actually use it to measure the pleasure that people experience when they view certain advertisements. So this study was done relatively recently, but it involved a television ad that was popular, a decade or so ago. It's called the 11:30 appointment Diet Coke ad. So here's the story. At 11:30 on a particular day in the middle of the week, a bunch of women gather in this room in a high-rise office building, and they all get out their Diet Cokes. And it isn't really clear what the meeting is about until the window washer shows up. This hunky, sweaty guy shows up and washes the window. And after he's done washing the window, he's all hot and sweaty, and so he refreshes himself with a nice cold Diet Coke. And all the gals are drinking their Diet Coke and really enjoying the show out the window. This was apparently a very successful ad. So what these researchers did was they hooked up a bunch of subjects, and these were adults, college age, but to almost middle age, and they recorded the electrical activity of their brains as they watched this ad. And the bioengineers were able to take those neural recordings and derive a measure of activity in the left frontal cortex and activity in the right frontal cortex, and here's what they showed. The green trace is activity in the left prefrontal cortex, and the red or brown is right prefrontal cortex in males and females. And the dashed vertical line is the moment in the ad when the sweaty window washer appears. And you can see in the men at that moment, activity in left and right prefrontal cortex was relatively low and equal. So it's as though the men thought, meh, so what? Not so in the women. In the women, when the sweaty window washer shows up, right prefrontal cortex has low activity and left prefrontal cortex has rather high activity. Down here in C, they computed the difference between the left and right prefrontal cortex activities. And that difference for men is shown in blue and for women is shown in purple. And you can see that when the sweaty window washer shows up, there's almost no difference in activity in left and right prefrontal cortex in the men, but a huge difference in the women. And this is correlated with the effectiveness of the advertisement, that women were motivated to buy Diet Coke by this ad, and it was correlated with difference in activity in left and right prefrontal cortex, left more active than right by a lot, which was proportional apparently to the happiness, to the pleasure they felt watching this ad. So what do these results tell us? Well, they tell us you can measure how happy people are with ads by measuring the activity of their left and right prefrontal cortex. And you can bet that this kind of research is still going on at many companies in the United States and probably also Europe and other parts of the world now. Does it tell us that all we need to do to be happy is drink Diet Coke? No, it isn't nearly that simple. We'll talk about that more in part 2.